All right, so talking about waves and some of the vocabulary that we need to talk about. Talking first about transverse waves. Let's get some vocabulary in there. Okay. First thing we want to do is we want to talk about amplitude. Amplitude is the height. So in transverse waves, this is referred to as the amplitude. Okay. So it's from the equilibrium point, the point in which it originally started off, all the way to the very top of the wave, what we call the peak of the wave. That's referred to as the amplitude. Okay, so this right here, from the equilibrium to the highest point, is called the amplitude. We can also call this the amplitude. So from the equilibrium to the trough, we can call that the amplitude too. The other pieces of vocabulary that we need to talk about, this right here is referred to as the wavelength. It's the point where the wave returns back to its original point. So talking peak to peak, I can even talk about this point to this point equaling the wavelength, where it's a wave heading down, crossing the equilibrium point. Not this point, because it's the wave heading up, crossing the equilibrium point. So we're talking about the next point, the wave heading down. That's also referred to as the wavelength, or even we can talk trough to trough. So, so wavelength is just a measurable distance. It's a distance from this point to that. So when we talked about electromagnetic radiation, we talked about radio waves, we talked about gamma waves. We were talking about this distance for the case of the radio waves being tens of miles. And when we were talking about gamma radiation, we're talking about a little bit bigger than an atom. A little bit bigger than a molecule as the wavelength. So it's pretty fast when you're talking gamma rays. It's pretty slow. You know, it's a low-beam wave. I mean, it still travels at the speed of light, but it doesn't travel very quickly in this direction. Okay? Now, in the case of longitudinal waves, so the motion of both of these waves are in that direction. So we're having the wave itself move in this direction. But in the case of a transverse wave, the matter itself, what the wave is composed of, is traveling entirely in this direction. Okay? So none of the matter is moving in this direction. Only the wave is. Excuse me. The matter is moving in this direction. So if I had a cup at the end of this catching my waves, catching the matter as being delivered by my waves, it's going to remain empty. Because that object is just going to oscillate up and down, not entering that cup, not delivering matter into that cup. Okay? Now, in the case of longitudinal waves, even though the motion of the wave is in this direction, the motion of the particles in the wave is in this direction. It's oscillating back and forth. And what I got here is kind of a diagram. So we've got a particle that goes out there and collides with another particle. Okay? That particle then moves on, and then it collides with another particle and moves on, moves on, moves on, moves on. So you get this net motion in this direction. Well, every time a particle collides with another particle, we have momentum being transferred. So this particle may move forward, but this particle is going to move backward. Okay? So it goes bang, and then collides with another particle, bang. So it's oscillating back and forth. So in a sense, you can think of this as a wave here, oscillating back and forth. Now this particle is doing the exact same thing. It's oscillating back and forth. Okay? So we have motion in this direction and motion in this direction. And the wave motion is in this direction. Now if we were to look at the bulk mass of this, we would get zones where you would have a lot of matter, because you would have 2 pieces or 4 pieces or 20 pieces in one section just about ready to collide. And then you have areas where it'd be really low in matter, and then areas that are high in matter again. Okay? So low matter area, high matter area. Now, the low matter area, so if this particle is collided with this particle, then I have a zone where there's no particles, a low matter area. Excuse me again. This area where there's no particles or very few particles, it's called rarefied. It's rarefication. You've rarefied the air, so there's very few particles. The particles are rare in this area. Okay? Very few. This area is called condensation, where matter has been condensed. So you have matter condensing at that point. I have this particle slamming into this particle. Two pieces of matter here. That matter is now condensed. I have a zone where it's condensed. I have it condensed, I have it rarefied, and I have it condensed. Okay? Cool? Now, referring to some of these terms like wavelength and amplitude, it turns out that the wavelength here, which is from the center of one condensed to the center of another condensed, or treating this region as rarefied, the center of my rarefication to the center of my rarefication, that's the wavelength. Okay? That's what we refer to the wavelength. So once again, we're referring to a zone to another zone. Okay? Now, it turns out that that's also referred to, not as the wavelength in the case of longitudinal waves is twice the amplitude. So from here to the center is what we refer to as the amplitude. Okay? So it doesn't really come out very clearly. Redraw that. So from here to here, so the center of rarefication to the center of condensation, that is the amplitude. Okay? So from here to here is the amplitude, from here to here is the wavelength. So in the case of longitudinal waves, only longitudinal waves, that the wavelength is twice the amplitude. Okay? Now, in this relation for transverse, there's no correlation between the amplitude and the wavelength. Okay? Cool? Now, in mechanical waves, we tend to say that the amplitude for a transverse wave is proportional. It has a relationship to its energy. So higher the amplitude, the higher the amount of energy is in that area. Okay? That doesn't necessarily hold true for longitudinal waves. That amplitude is directly related to the wavelength. As a matter of fact, in transverse waves, we tend to measure intensity. We tend to measure the amount of energy that those particles are delivering. Now, I've talked about the cup in transverse waves catching matter as it goes from that point to that point, and finding out that my cup remains empty because the motion of matter is in this direction, so that cup. Now, in the case of longitudinal waves, my cup is still not going to catch anything, but what ends up happening is I would have matter enter the cup and then leave the cup, enter the cup, then leave the cup. Okay? So I have matter entering the cup all the time, but it's not staying in the cup. The net mass that it gains is zero. It doesn't gain anything. There's no matter being delivered to the cup. It just simply holds it briefly, and then it's kicked out. Okay? So that's a basic rundown of transverse and longitudinal waves with some definitions. Cool?